Single switch high boost non-isolated DC-DC converter. Abstract: the major classy.cation of the DC-DC converter is isolated and non-isolated converters depending on high voltage conversion ratio. The high voltage gain is attained by changing the turns of the transformer. One of the main features of this converter is which can provide a high step-up voltage conversion ratio within a moderate duty cycle and also improved voltage gain. To minimize the voltage stress across the semiconductor devices, this converter utilizes the properties of SEPIC and boost converter with diode capacitor circuit. This converter uses MOSFET switch with reduced switching and conduction loss. The single switch high boost non-isolated DC-DC converter can produce low switching voltage, so it can improve its efficiency. The converter simulation is done in MATLAB/SIMULINK R2017a environment. Arduino microcontroller is utilized for the switching pulses of this control circuit. To verify the performance and operating principle, output voltage of 390V and input voltage of 30V with output power of 390W prototype is constructed and the results are validated. Keywords: boost converter, MOSFET switch, SEPIC converter, high voltage gain, non-isolated DC-DC converter. Introduction. Renewable energy is increasing enormously and plays a very crucial role in the production and distribution systems. In environment, the photovoltaic sources are capable of producing low voltage DC, and hence it is not appropriate for direct connection to microgrid. Hence, to increase the voltage level, PV modules are connected in series way. The usage of DC-DC converters are not only overcome this drawback, it is also very helpful in boosting the low voltage level to high voltage with good efficiency. It's helpful in utilizing renewable energy in a better and efficient way. The main and important features of high step-up converters are their large conversion ratio, small size, and high efficiency. The main classy.cation of the DC-DC converter is isolated converters and non-isolated converters based on high voltage conversion ratio. The isolated converter type model has a transformer model in it. The high voltage gain is obtained by means of adjusting the number of turns of transformer. Under this type of classy.cation of non-isolated converters, conventional boost converter delivers high voltage gain ratio with large duty cycle, resulting in large switching voltage stress, which in turn lower the efficiency and produces very large inductor current ripples. In order to improve conversion efficiency and to obtain high step-up voltage gain, many DC-DC converter topologies are developed and implemented. A property of switched capacitor and voltage lift techniques has used to obtain high step-up voltage gain ratio. But, in these structures, high charging currents will circulate through the main switch, and thus it leads to the increase in conduction losses. By adjusting the turns ratio, coupled inductor-based converters also can obtain high step-up voltage gain. Switched capacitor is aligned at the switching condition of the DC converter to get improved voltage ratio with required duty cycle. But one major drawback of this technique is, a pulsating input current is produced, which causes to load problems and poor line in the system. Fig. 1 Single switch DC-DC converter. S. Saravanan and N. Ramesh Babu proposes a DC-DC converter which has high voltage gain even using a single switch. There are 4 modes of operation. In mode 1, the switch S is turned on, diode D3 will be in conducting state and diodes D0, D1, and D2 are in blocked state. Inductors L1A and L2 and capacitor C1 get charged. This mode terminates when current in diode D3 becomes 0. The switch S's continue to be in on state at mode 2 and diodes D0, D1, D2, and D3 are in block state. Inductor L1 get charged from the input side. As D is in block state, capacitor C0 supplies current to output resistor. When the diode D2 starts conducting, then this mode ends. In mode 3, the switch S is in on state and diode D2 is in conduction mode, and diodes D1, D3, and D are in block state. L1A and L2 get charged. The capacitor C1 gets charged though diodes. This mode of operation ends when current in diode D2 becomes 0 and switch S is turned off. The switch S is turned off at mode 4 and diode D2 will be in block state, and diodes D0, D1, and D2 are in conduction mode. Inductors L1A and L2 get discharged. The capacitor C2 is getting charged. When the main switch S is turned on, then this mode of operation gets completed. In order to improve the voltage gain of the circuit pointed above, modified the circuit by adding a capacitor in the input side. By adding this, it is observed that the gain can improve to 13. There is no any difference in designing aspects. 2. Proposed converter. Proposed non-isolated single-switch high-step-up DC-DC converter is shown in Figure 2. It consists of 2 inductors, L1 and L2, 4 power diodes, D0 D3, 5 capacitors, C0 C3 and Cm, 1 power switches, S, and a resistive load, R. Fig.2, Proposed converter. The following assumptions are taken consideration while designing the converter. 1. All components are taken as ideal and lossless. 2. Frequency of the switches are kept constant. 3. Capacitors are designed in such a way that ripple voltage across the capacitor are low. 3. Operating principles. The working of the circuit can be explained by the given 4 modes. The given figure, 3, 4, 5, 6, shows the operating modes of the converter in the CCM. Mode 1. In this mode of operation, the switch S is in on state, and diode D3 is in conduction mode, and diodes D1, D2, and DO are in block state. The energy will store in both inductors during this operation. The input voltage makes the capacitor C1 to charge the capacitor C3. The input capacitor Cm will get charged. Output capacitor CO gets discharged at this stage so that output load gets energy. This operation completes when diode D3 current becomes 0. The switch is continued to be in on state. Diodes D1, D2, D3, and D0 will restrict the flow of current, i.e., block state. Inductor L1 and input capacitor Cm get charged at this stage. When the diode D2 starts conducting, then this mode of operation finishes. The switch S is on at this mode and is shown in Figure 5. Diode D2 is in conducting mode. The diodes D1, D3, and DO are in blocked condition. The capacitor Cm will get charged. Inductors L1A and L2 and the C1 capacitor are charged through the path diode D2. When current through diode D2 becomes 0 and the main switch S is turned off, then this mode of operation completes. Mode 4. In this mode of the operation, the switch S is in off state. The diode D2 is also in off condition and the current flows through diodes D1, D3, and DO as shown in Figure 6. Fig 6, Mode 4. The inductor L1 and inductor L2 will discharged and capacitor C2 is charged at this stage. Also the input capacitor Cm will discharge the energy. When the main switch is turned on, one period of cycle ends. 4 design considerations. A. Inductors. The value of the inductor L1 and L2 are calculated as per the given equations. V. Simulation results. The simulation parameters of single-switch high-boost-up non-isolated DC-DC converter is given in the below table. An input voltage VEN of 30V gives an output voltage VO of 390V for an output power PO of 390W. The simulation results of proposed converter is shown in the .grs. The switching frequency is 24 kHz. The gate pulse of main power device has .xed duty cycle of 81%. It can be seen from the Figure 8a, and Figure 8b, and 8c, that the output current is 1A, the output voltage V0 is about 390V and output power is 390W. As shown in Figs 8d, and 8e, the voltage of the capacitor C1 and C2 is boosted to 200V. 6 Analysis. AE.CNC vs output power. E.CNC is an expression of the effectiveness exhibited by a machine to deliver as per its design. It is simply defined as the ratio of the power output to the power input. From this analysis we can understand that how much input power is delivered to the load. Figure 10 shows E.CNC vs output power graph. Fig.10, E.CNC vs output power. B gain vs duty cycle. A typical curve represented below shows the voltage gain as a function of duty cycle. From the .gur 11, we realize the fact that the voltage gain is 13 when the duty cycle is equal to 0.81. 7. Conclusion. The single-switch high-boost non-isolated DC-DC converter O.ERS a high conversion ratio, low switch voltage stress. The result of the design shows that the switch and diodes have relatively low voltage stresses and hence the switching and conduction losses are reduced. And as a result of this it achieves an improved overall E.CNC. In this the input voltage is 30 V and the output voltage is 390 V, this shows the high step-up voltage gain. The proposed converter has an E.CNC of 94% and voltage gain of 13. To limit the voltage stress across the switches and diodes, we must maintain a duty ratio of 0.81. The overall analysis and results shows that the converter can be used for applications with low input voltage and high output voltage, such as battery chargers, distributed power systems etc.